God morgon alla kära konferensdeltagare i Biogas 2021 Guldruschen. Igår hade vi en jättespännande dag när vi fick höra om vad är det för någonting som behöver vara på plats när regioner ska utveckla biogaslösningar. Vi fick ett ordmål som ni producerade där det stod sånt som långsiktighet, politisk vilja, samverkan och många andra bra förslag på faktorer som spelar roll. Sen var jag med på sessionen som handlade om utvecklingen inom flytande biogas. Och den andra sessionen var ju inriktad på vad kan vi göra för att fortsätta att växa inom transporter och så med komprimerad biogas. En jättebra dag, jättekul att veta att ni är 350 personer som sitter där ute och lyssnar. Och idag ska vi kickstarta rejält med att också fundera över det som händer i Sverige, hur förhåller sig det till vad som händer i resten av världen. Så jag har bjudit in en kär kollega från Irland, Jerry Murphy, som kommer att hjälpa oss med det här under det första passet. Jag vet inte om vi kan få med Jerry i sändningen. Good morning, Jerry.
Good morning, Mats.
So how are you there? I haven't really introduced you properly yet, so I just thought maybe we could start by saying that you are a professor from the University College of Cork in Ireland, and the reason why I asked you here was that you have also been chairing the International Energy Agency Task 37 for some years. And for those of you who don't know that organization, it means that 25 member companies share their experiences in research and what is going on in terms of development in the biogas field. And Jerry has led that. So I guess you're quite well positioned to help us with this bigger overview of what is happening in the biogas field and maybe related to Sweden. So what do you say about that introduction? Maybe you want to add something, Jerry.
No, you introduced very well, Mats. The role of IEA Bioenergy is to disseminate as much of the good stories that are available across the member countries. And we try to have an international perspective. We produced reports on biogas, for example, in Africa and Brazil. So we try to get the big perspective. I mean, we're aware that Sweden and Germany and Denmark were leaders, but we're trying to get other perspectives of other countries who don't have incentives.
Yeah. So please, we want to thank you for getting up early, spreading your wisdom together with us here, and let you start your presentation. And then we'll see afterwards if there are any questions from the audience, or maybe if I have a question or two to clarify. So the screen is yours, Jerry.
Thank you, Mats. Greatly appreciated. As a brief introduction, I lead IEA Bioenergy, and I've been in that role for, I think it's 6 or 7 years. I'm also director of the MARI Centre for Energy, Climate and Marine in Cork. And Mats is on our Science Advisory Committee. We are about 250 people, lots of different research going on in energy, climate and marine. So bioenergy and biogas is probably a seventh of the output, but we do try to have an integrated perspective across the whole energy climate sector. If I start off a little bit in defense of bioenergy, and there is a perspective abroad that we shouldn't burn anything and everything should be electrified and it should all come from wind turbines and PV. You're probably aware in Sweden more than other countries that modern bioenergy is about 50% of all renewable energy. So if there is this perspective of electrifying everything and not burning anything, it takes us a long way back. And if we look at renewable heat and we look at renewable transport, we can see they're dominated by bioenergy. Just going back a little bit to look at what the problem is, the IPCC state that we have a carbon budget of 800 gigatons of carbon. And every piece of carbon we release is important. So there's no point coming to 2040 or 2050 and saying we're going to decarbonize now. Every piece of carbon we emit needs to be managed, needs to be reduced. And the perspective is that we should be down beyond 2060 to zero carbon, which may not be sufficient. So there's also this perspective of negative emission technologies. And this is something that is built into a lot of modeling, that we will come up with a mechanism to take CO2 out of the atmosphere at a large scale to allow us to continue with, for example, farming. 30% of greenhouse gas emissions in Ireland come from farming and belching cattle, and it's very hard to decarbonize a cow. It's very hard to decarbonize planes. It's very hard to decarbonize ships that go from, say, Stockholm to Shanghai. So there are sectors of the economy which are difficult to decarbonize, and there is a perspective that bioenergy with carbon capture can be a solution. And very simply, the idea is that we grow a crop, maybe a willow or a miscanthus. It goes into a power plant, produces heat and power, and the CO2 is captured underground. So this would be seen as better than a wind turbine, because you're getting carbon neutral energy, but you're also capturing the CO2 and putting it underground. So the IEA and the IPCC see this as a very important element. And this to me is quite a simplistic perspective. There's other ways of looking at how bioenergy can be greenhouse gas negative and how it can capture more CO2 than it releases. When we look at this concept of electrifying everything, that we're still going to have agri-food treatment. So this is Linköping, and I have been going up to Linköping since the 90s. I think I visited Linköping maybe 8 or 9 times at this stage. It may have changed from the last time I was there, but I use this as a lovely circular economy system. You have slaughter waste, you have slurries. Slurries would produce methane that goes to the atmosphere. If you're plowing slaughter waste into agricultural land, you're going to contaminate water. So this system is environmental protection and production of biogas as a transport fuel in a circular economy system. So you're cleaning air, cleaning water, and providing renewable transport fuels for waste collection lorries, buses, cars. And when we continue to look at more difficult sectors, we're doing a lot of work at the moment in my research center on alcohol, and we're looking at distilleries and breweries across the planet. So we're doing work in Mexico, in India, and in particular, we have a very, very large distillery where I live. It's the 4th largest whiskey producer on the planet. And at the moment, they have about 36 megawatts of gas boilers going all the time to evaporate alcohol from stillage. And we've been looking at, well, these are areas that biogas is very useful to decarbonize. So if we capture the draft, the stillage, the pot ale, we can make biogas. The biogas can replace natural gas. And we found that typically we could replace maybe 60% of the emissions. And typically in an industry, you have scope 1, which is the emissions on site. Scope 2 would be if you have electricity coming from an off-site source. Typically, we use wind power in Ireland, so that isn't an issue. Scope 3 is the fertilizer, the grain, and the delivery of the grain to the facility. So the discussions we're having is we can reduce Scope 1 by 60% by displacing natural gas, but we could also put that biogas into the trucks that bring the grain to the vicinity and reduce Scope 3. And if we use the biogas for transport, we get over 10 cents a kilowatt hour. If we use the biogas for heat, we're only getting 2 cents a kilowatt hour. So we actually have this multi-criteria objective analysis type system to figure out what is the best way for the distillery to decarbonize. Within IEA Bioenergy, we do a lot of case stories. We produce about 8 large reports every 3 years and maybe 16 case stories. So these are just 3 I picked. One is an organic farm in Denmark. So the farmer did not have fertilizer because it's not permitted. He had a dung from the cattle, which doesn't spread. So the biogas facility was used to make a biofertilizer that would mineralize the nutrients, that would be liquidy and could be spread, and also produce biogas. But that farm is now certified as minus 0.82 kilograms of CO2 per litre of milk produced. So this shows again how biogas can give you a negative greenhouse gas footprint on a whole life cycle basis, because you don't have slurry going up into the atmosphere. You don't have chemical fertilizer coming onto the land. We've also looked at a brewery in Austria, the Gosser Brewery, which deems itself to be carbon neutral through biogas. And they also have wood chips, so they've eradicated Scope 1 emissions. Now, they may still have Scope 3 emissions, but from their perspective, they've eradicated Scope 1, they're carbon neutral. And then our Brazilian partners have a campus where they had 400 hectares of grassland around their campus. And they've used that grass in a digester to make transport fuel for cars on the campus. So these are little circular economy case stories that we would highlight in IEA Bioenergy. We're also quite closely connected with IEA, with the head office in Paris. And this is a report I gave guidance on. And this is the outlook for biogas and biomethane from IEA. And you can see we have an actual production of 35 million tons of oil equivalent. And IEA's perspective is we have a potential of 730 megatons oil equivalent. So we're looking at, from the perspective of IEA, we have a lot more resource. Now, Sweden is a world leader, so I've no doubt that Sweden has capitalized a lot on its resource, but we're looking across the planet. And one of the things they have said is that we really need to go after biomethane. And biomethane would then be used as a displacement for natural gas. And what they mentioned was, in the US and in Europe, we get over 100% more energy from the gas grid than we do from the electricity grid. So there is a need for us to green the gas grid. This is a large technical report we did, led by Jan Liebertrau in Germany, where we looked at methane emissions from biogas plants. So there was a survey of plants in Germany and in Sweden, and they looked at where slippage came in biogas plants and how it could be minimized. But in brief, what we found was that it's quite easy to get below 2% slippage. And if you're below 2% slippage, your do-nothing scenario is open slurry tanks where 17.5% of the methane potential goes to the atmosphere. So if your biogas can keep slippage below 2%, you're probably saving over 15% of methane going to the atmosphere at a global warming potential of 28. So we did this work with the JRC in Petten, and we found that we were about minus 250 grams CO2 per megajoule, which ties in with the California Air Resources Board, who awarded a carbon intensity of minus 255 grams CO2 per megajoule for a dairy waste to vehicle fuel pathway. So again, by dealing with wet organic waste that is producing fugitive methane emissions and incorporating that into a biogas system on a whole life cycle basis, we can be greenhouse gas negative. And when we look at this large resource that the IEA are talking about, our perspective is we need to go into the distilleries, the infant formula, the cheese plants, and capture that resource. So we've looked a lot at renewable electricity. Our perspective is now we can look at green gas, and we're looking at anaerobic digestion, and we're tying in seaweed and fish farms, and I'll briefly overview this. We're looking at gasification to a little bit, and we're also looking at power to gas and electrofuels and tying together electricity and gas and also water, which I'll explain. If we look at the extent of biogas upgrading over the last number of years, it's growing really fast. And it's been driven by Germany. Obviously, Sweden is there. The United Kingdom has only come into this game in the last 7 or 8 years, but is a major player now. So a perspective is out there that this can be a technology applied to other countries where we put gas from wet organic material or from electricity or from gasification into the gas grid. And this is just one system we looked at in the Netherlands, where the biogas plants pump biogas to a hub, and the hub only gets biogas and upgrades that biogas using water scrubbing, pressure swing absorption, membrane, and they can sell carbon dioxide. So we have another case story in Denmark where one biogas plant supplies 25% of the CO2 market in Denmark. And the CO2 market in Denmark is 65,000 tons a year. So we're looking now at centralized hubs selling CO2, putting methane in the gas grid and having liquefied biomethane. I won't spend long on this, but this is actually, I believe, is in Gothenburg, Gobi gas. So we can gasify woody crops and also put that in the gas grid. We've done a lot of work in our group on seaweed, and it's another area that's of interest because we have bays in Ireland which have ulva lactuca. It's a horrible, ammoniacal, sulfuric. It gives off smells in the summer that has to be taken off the beach. And we found in France, in Lannon Bay, we can have 100,000 tons of ulva arriving. It's upsetting the oyster market, so it is it causes pollution on beaches. So we see this as another source. And we've also started looking at nicer seaweeds such as Laminari digitata. Our perspective is we can grow seaweed in waters that are suffering from water quality, improve the water quality. We can grow seaweed around fish farms, and the seaweed can be used for extracts such as alginates and phenols, and the byproducts can then go to biogas. And we have a case story in Denmark of the Solrod biogas plant, which digests beach cast seaweed and the extract from a seaweed biorefinery. We're also looking at microalgae upgrading biogas, and we're doing a lot of work in our own laboratory. So we're looking at a carbonate bicarbonate upgrading system, and the microalgae use CO2 in the carbonate bicarbonate system. So what we're hoping is that in a future scenario in coastal areas, we can have farmers making cheese, making beef, but also making biogas, which can be used for transport fuel, maybe taking seaweed off beaches, but also producing microalgae in a biorefinery. And our hope is they can make more money out of the microalgae than they can out of the biogas, which is all additive to what they were making from farming. So microalgae, my colleagues in Sweden sell compressed microalgae in tablet form, and they sell 50 tablets for 25 euros. So we're hoping that farming, anaerobic digestion, biorefining can all come together and improve the lot of rural coastal farmers. An area where we're doing a lot of work at the moment, and there's a lot of impulse, is the electrofuels. There is a perspective in, for example, in Ireland, that we're having auctions at the moment for up to 4 gigawatts of offshore wind to be put in place by 2030. At the moment, our electrical capacity is 8 gigawatts. So we're putting in 50% more electricity provision in the oceans of Ireland. And Ireland has had some of the highest levels of non-synchronous penetration. Because we're an island, we're not interconnected to Norway or Finland. We are an island grid. We've managed to have over 75% of the electricity at any one time coming from intermittent resources. But when we have 70% on average of electricity coming from wind turbines, it means at times we will have 175% of average demand coming from wind turbines. So we need a battery. And the perspectives we have is that hydrogen is a way of storing that electricity. And we've done a lot of work. A perspective we have is that you can't run an electrolyzer for 3,000 hours a year, which is very cheap. This is the electricity that would be curtailed because the electrolyzer would be too big. So our perspective is you need the electrolyzer operating over 6,000 hours a year. You bid at 6 cents a kilowatt hour. On average, you'll be paying about 3, but you bid at 6. And that gives a levelized cost of energy of 100 euros a megawatt hour. which is a litre of diesel equivalent. So we've come up with a methodology, a high wind forecast, a low electricity cost that allows us to get all that nighttime electricity and the curtailed electricity. It allows us to use electricity which is 57% more decarbonised than the electricity on the grid, and we can reduce the cost. Now, we've also done some work in Sweden with colleagues, and Sweden has a very different electricity grid, and this process varies from country to country. But our perspective is we're not going to get hydrogen less than €4 a kilogram, which is about €1 per litre of diesel equivalent. So hydrogen will be expensive. We are looking at this idea of a hybrid model that we will have large offshore wind farms that will sell power to the grid, but when the price is low, they will convert to hydrogen. So we'll have a hybrid model of electricity and hydrogen. I have a PhD student at the moment looking at electrolyzers on a platform in the ocean, looking at it on land, and looking at methodologies to optimize this system. We can then go on to methane. So this is Wörtel in Germany, and there is a food waste digester in place. They have a 6 megawatt electrolyzer. In the north of Germany, there's a lot of electricity. So the electricity is spilled to the electrolyzer, and they have a Sabatier reaction. So 4 hydrogen from the electricity, CO2 from the biogas facility, giving us methane and water. So in essence, all the carbon dioxide in the biogas can become methane by using electricity that could have been curtailed. So we've been looking at this from a biological perspective because we tend to work in the biological area. If we put an electrolyzer next to a biogas plant, and Europe has probably 18,000 biogas plants, if all of those had a little electrolyzer, we could add hydrogen into the anaerobic process and make methane and increase the output by 70%. It's not that easy to have an in situ process because you have acetoclastic methanogens who produce CO2. Our perspective is we can have a partial upgrading in the existing digester, and then we have an ex situ system. And out here we have hydrogenotrophic methanogens. So we have bugs that eat hydrogen and carbon dioxide and make methane. And we've isolated these bugs in our lab. So we see surplus electricity as a means of upgrading biogas and increasing the output by over 70%. And this is a process we've developed in our lab. It's a sequential batch system. So we've been adding hydrogen and carbon dioxide. We need to get that hydrogen into solution, so we have recirculation. But we have a series of reactors until we get pure methane in the output. And we've spent a lot of money on developing this rig. So we're testing this guy at the moment. So these are our sequential batch reactors. And we're looking at adding carbon fiber and pyrochar. And this is something that we find interesting. We've done a lot of work on what we call direct interspecies electron transfer. We can add conductive materials to a digester, which make the process go faster. And they're little electron bridges. So we can make the anaerobic process faster by adding electrons, by adding conductive material that are a bridge for electrons. And we've taken this a little further. When we're looking at really big digesters, such as for whiskey facilities, we will have digestate. Digestate needs a lot of land. So we've looked at an alternative of pyrolyzing the digestate. So we segregate the digestate into liquid and solid. We pyrolyze the solid. We make syngas and bio-oil, but we make pyrochar, which is over 80% carbon. And that pyrochar is a conductive material which can make our digester smaller and more efficient. It's also very good in biomethanation. It helps the hydrogen go into solution, and it's a little film for bacteria to grow to. And when it goes back on land, eventually, it is a negative emission technology. It takes 100 years to make 4 mil of soil. This is almost pure carbon. When we put it on the land, it increases the soil organic carbon and pulls more CO2 out of the atmosphere. So we see the integration of power to gas, making hydrogen, selling oxygen, of pyrolyzing digestate, and of increasing soil organic carbon. So we're looking at these circular economies that are greenhouse gas negative and are carbon negative systems. We've been working in the Lower Harbour in Cork on a wastewater treatment plant. And what we have in the Lower Harbour, it's a very wealthy area. We've lots of pharmaceuticals. They've all put up wind turbines. There's lots of electricity that isn't sold. So by putting an electrolyzer at the wastewater treatment plant, the oxygen can go into the wastewater treatment plant instead of air, reducing pumping costs by a factor of 5. The sludge goes into an existing anaerobic digester, but the idea is that the hydrogen from the electrolyzer can be used in our ex situ biomethanation to upgrade the biogas to pure methane. So rather than having, and this is our system, rather than having biogas used for heat at 2 cents a kilowatt hour, we can increase the resource by 70% and make biomethane at 10 cents a kilowatt hour. And we're also looking at pyrochar to improve the biomethanation and to go back to land. So we're looking at an application of our research to the Lower Harbour, to the existing wastewater treatment plant, to the existing wind turbines. And it's a nice circular economy system. We can also go further than methane. This is a plant in Denmark, and they're looking at methanol. So we can now have anaerobic digestion producing carbon dioxide and methane, but we can reform that and eventually have methanol, which is a liquefied alcohol which we can use to run cars or trucks. The stoichiometric output of biogas isn't ideal for methanol. It's 3CH4 plus CO2, so it depends on 75% methane and 25% CO2. But when we introduce hydrogen from an electrolyzer, we can have complete conversion of biogas to methanol. And Porsche are building such a facility to make methanol to power all their old classic Porsches. But when we start looking at aviation and shipping, we need to go towards liquid. So this is a proposal in Germany for a very large electrolyzer system, taking offshore wind in the North Sea, making oxygen, which will go into a cement factory. The CO2 from the cement factory will be captured and reacted with the hydrogen from the electrolyzer to make methanol, as we just described. And that methanol can then be brought to kerosene and used for aviation fuel. So we're now going from offshore wind, district heating, green cement, and aviation fuel. This is the facility in Denmark. As you know, Denmark has a number of very large digesters. They're looking at incorporating power to gas. They're also looking at putting pyrolysis of the digestate at these facilities. So we're looking at a big circular economy system, taking excess power from the electricity grid, digesting wet organic feedstocks, pyrolyzing digestate, making pyrochar, putting pyrochar back on the land, and optimizing the system. So that's the end of my presentation. I hope it was helpful. I have to thank all my funders, obviously, IEA Bioenergy and Science Foundation Ireland and others. So I hope that was instructive, Mats. I'll stop sharing my screen if that's okay.
Thank you very much, Jerry. I think it was a very rich presentation. I think there were a couple of things that maybe I'll try to just share a couple of my reflections if you want to follow up there, Jerry, because I think that what we learned about here, I would say, this idea that we cannot electrify everything is, of course, one very important thing. Maybe it's even rather that we are going to not use the fossils, so we will still need a lot of food, feed, and fiber, which means that we will have to work a lot with carbon-rich biological material, and there will always be room for a biogas solution there. Some other things that I really caught in your presentation, I think that the negative emissions showed up here and there. I think maybe in the future that's probably where we want companies and others to head and try to be focused on that. A lot of interactions between different parts of the energy system. That's another area where I see you're doing. But I think what you are also sharing that maybe not most people don't know is that we haven't maybe come very far in terms of the technology development. I don't know if you want to comment on that. I guess there is so much improvement that we can do. Isn't that so, Jerry?
I think it's very exciting. I mean, I am an academic, and the role of the academic is to look 10 years ahead and say, well, what will it look like in 10 years' time? And to me, I'm very excited by seaweed. I'm very excited by the biorefinery, taking out extracts, using the byproducts within the digester. I think power to gas will become very, very important. We are looking at a lot of surplus electricity that will be very, very cheap. And to me, we can pull that into the bioenergy system. I think soil is huge. I mean, soil organic carbon. And I think the perspective of the biogas industry is we have to bring other people with us. We have to bring agronomy, there's microbiology, there's the process engineering. But I think the cascading system, incorporating and pulling together electricity, gas, water, the creameries. I mean, Ireland produces 15% of the world's infant formula. We have lots of wet organic waste, the distilleries. We have to have a broader lens. We need to look at cheese. We need to look at alcohol. We need to look at food waste. We need to look at seaweed. We need to talk to our gasification colleagues. It needs to be an integrated system.
Thank you. We are on a very tight schedule, Jerry. I think we need to stop here. I would have liked to talk to you about this for an hour or so, but let's just conclude that anyone who wants to know more, we will happily get you in contact with Jerry and all the other parts of the world. Even Sweden have a representative in the International Energy Agency Task 37. So there are ways of reaching out to the international audience. If we want to share something about what I try to call the Nordic model, or if we want to capture a lot of the interesting stuff that is going on in the world. So thank you very much, Jerry. It was a pleasure.
Thank you, Mats. Thank you for the invite, and thank you for supporting us in Marai.
Bye.
Ja, projektet är helt enkelt att göra någonting med vår gödsel, att kunna göra energi av den. Va? Och vi hade väl kanske i vår startlinda diskuterade mycket om skog och så. Va? Men så kom vi ju fram till att alla hade väldigt mycket gödsel och att man kunde använda den och vidareförädla den då. Va? Och det har varit väldigt roligt för att alla liksom har litat på alla och trott att alla har gjort sitt bästa i det här projektet, kan man säga. Så det gett istället en tilltro till bygden. Alltså, många av de här gårdarna har byggt ut sedan dess och alltså vuxit och blivit effektiva företag efter det här projektet. Va? Största utmaningen genom hela projektet, det var att få banklån. Att få någon bank att gå med oss. Vi var runt på, tror jag, nästan alla banker som finns. Och nästan alla, i stort sett grinar åt och så. Att få den lönsam är ju givetvis att man har fått till ett gaskontrakt ju, som är viktigt ju. Och då hade vi vårt lokala projekt här med småländska bränsle. Det andra var att länstrafiken i Växjö, just när vi skulle bygga den anläggningen, beslutade om att 44 bussar ska gå i Växjö. Det gjorde att det fanns utrymme för att bli av med gasen. Vi har en fast anställd här som jobbar från morgon till kväll, och sen har vi 7 stycken killar då som beredskap som har var 7:e vecka, som har nattjour och helgjour. Och så att det är unga killar, flera av dem är bonnakillar kan vi säga, som tar natten då. Hela anläggningen kör man ju fjärrstyrt från telefon och så här, va. Men visst, det är många nätter de får åka hit också. Alltså det fina med sådana här projekt är ju att det är så bra för hela kedjan. Alltså all gödsel från lantbrukarna går genom grinden och sen så, och vi kan ju säga att vi bara lånar gödseln. Och lika många kubik som vi hämtar från bonden får bonden tillbaka, och han sprider det på sin åker och det växer. När han får tillbaka den så har den så här 10-25% mer näring i den än när vi hämtar den, och det beror på att värmeprocessen och lignin och sånt har varit utsatt för värme, så kommer växten åt mer näring. Vi använder inte alls all substrat som vi har tillgängligt nu, för att många av lantbrukarna har byggt ut och blivit större, och så vi har oerhört gott om substrat att växa. Utan vad som krävs det är att regeringen ger rätta villkor mot Danmark. Idag är ju oerhört mycket gas som tankas våra bilar är dansk. Det andra är ju att våra politiker och allihop gynnar bilpark för biogas ju. Så att vi kan teckna nya avtal och få iväg mer gas. Då investerar vi. Det är inga problem. Det som jag skulle vilja tala om är ju att detta lilla som man tycker ändå är ett rätt litet Alvesta biogas förser gas till 2000 bilar. Det är rätt fantastiskt. Gjordes en utredning nu i förra veckan från SLU där man tog fram biogas från gård då alltså. Där man fick 115% förbättring av koldioxiden alltså. Så alltså det är 15% bättre än att cykla att köra biogas från Alvesta. Och då kan man tycka, varför detta nu då? Och det är ju för att man tillgodoser att inte man har några metanutsläpp på gårdarna längre. När vi sprider gödsel, så att kommer man ju till de här extra 15 då.
Det går till som så att man börjar någonstans långt tillbaka och inser då att men vi har en massa gödsel, vi har en massa kor, kan vi göra någonting av det? Och sagt gjort så byggde vi ju en rötkammare och vi producerade el och värme sedan 2012. Elpriset sjönk, vi såg lite att kan vi få någon bättre lönsamhet i det här? Så vi började ju redan då titta på kan vi få till en fordonsgaslösning på något sätt. Det fanns ju flera alternativ men det är liksom på något sätt kunna förädla gasen. Väldigt lång historia kan vi göra kort. Till slut, tack vare Kalmar länstrafik, stor upphandling med bussarna, så fanns det ett behov av gas 2017. Vi hittade ett samarbete med E.ON som är vår samarbetspartner i det här då, där vi kunde leverera gas till dem, och tack vare också Klimatklivet och Naturvårdsverket att de typen av investeringsstöd fanns, så hade vi ju möjligheten att överhuvudtaget kunna gå framåt med de här planen. Sen ville vi öka den volymen, så vi ville gå från 7 GWh upp till 12. Men det var ingen som ville bygga mackar i närområdet för det finns ingen marknad. Och till slut fick vi väl bygga dem själva helt enkelt. Att skulle det hända någonting så var det vi som fick driva på det också då. Så då byggde vi en 5 km lång gasledning in till Målilla, där vi sätter en moderstation. Moderstationen ska då dels kunna publik tankning också, men också för att kunna skeppa gas därifrån till dotterstationer i Vimmerby, Hultsfred och Högsby. Det skulle underlätta och kunna vara ett hinder också. Det skulle underlätta distributionen väldigt. Att hade man en gaspipa som man kunde skeppa iväg all gas på, så hade ju det varit smidigt. Då behöver man ju inte lika beroende av att logistik och lastbilar och flak och allt det här ska synka och funka och allt så här, utan då där du producerar det kör du ner och sen kommer du upp där det ska. Så rent distributionsmässigt så är det super. Nackdelen blir ju då att vi liksom förbrukar ju dubbelt så mycket biogas som produceras i Sverige, och den är importerad. Och då hamnar vi lite där det inte är samma produktionsförutsättningar i ett annat land som i Sverige. Då är ju den importerade gasen billigare, och då är det svårt för oss att konkurrera med den. Utmaningarna har väl varit väldigt många egentligen. Vi är ju, vad jag vet, Sveriges minsta privatägda uppgraderingsanläggning som ägs liksom av en part privat. Bara den, alltså skala ner processen så mycket så att det liksom går att hitta en lönsamhet i det är lite svårt. Vi har fått hitta andra vägar, kanske de inte som normalt kanske finns, men vi har fått leta och hitta balanser, hur vi har byggt, hur vi har tänkt, hur vi har format anläggningen. Vi har ju och behöver också ha stor draghjälp av kommunerna, att de ställer om bilparker och liksom promotar och hjälper till och supportar. E.ON har ju varit en del i det här också, som har gjort att vi kan hitta ett samarbete för att ha en större aktör med oss också. Det krävs en väldigt kontinuerlig avsättning. Det är svårt att lagra gasen. Vi kan producera den och vi kan förbruka den, men ganska fort så uppstår ju liksom vart problemet var man ska stoppa den då. Så vi hade ju inte kunnat gå i mål med det här om inte vi hade haft en aktör som vi kunde leverera kontinuerligt till. Framöver, vi behöver få upp volymerna på mackarna framför allt. Vi har ju räknat med att det ska gå back de första 3 åren typ, tills marknaden har kommit så stark att vi kan omsätta i princip så mycket gas så att varje mack bär sig själv. För då har vi nått ett steg på målet. Så vi hoppas ju och tror ju att det här, världens bästa miljöbränsle då, lite färgade får man väl säga, kommer fortsätta öka, och liksom att på sikt så kommer det här vara en större del av trafiken som kan gå på det här. Om det är bussar eller bilar eller vad det nu må vara.
Ja, då har vi fått både till livs lite grann av vad som händer i den här regionen och fantastiska entreprenörer. Och vi har fått höra Jerry Murphy berätta om att det är oerhört mycket spännande på gång när det gäller teknikutveckling och den globala utvecklingen. Hoppas alla är igång, startade ordentligt med den här morgonen. Nu tar vi en kort rast och vi är tillbaka 9.20, och då vet ni, då är det 2 spår man kan välja på. Och det ena spåret heter Mer biogas i praktiken, handlar om produktion och konsumtion. Och den andra heter Biogas, den bästa 10-kamparen, och kanske handlar lite mer om hållbarhetsperspektivet på biogas. Så hoppas vi ser det träffas där också. Tack ska ni ha.
Alla vet att fossila drivmedel skadar både människor, natur och klimatet. Vi kan inte fortsätta med det. Lyckligtvis är det enklare att byta till ett prisvärt och rent alternativ än man kan tro. Ja, även för dig. Vi har bara hållbara drivmedel här hos oss på Orange Gas. Vi har biogas, HVO 100 och vätgas. Vi har också flytande koldioxid som kylmedium och snabbladdare för elbilar. Orange Gas arbetar hårt varje dag för att hållbart körande ska vara möjligt för alla. Vi hjälper företag och enskilda som vill köra hållbart för att hitta rätt med sina drivmedelsval. Vi bygger nu ett nätverk av mackar i Sverige där du kan tanka rena drivmedel och minska föroreningarna. Kanske är vi snart hos dig. Tillsammans är vi på väg till en gladare planet. Tänk positive. Orange Gas.
Biogas production and use are part of the circular economy. Biogas is 100% renewable energy produced from biodegradable industrial, municipal, agricultural, and household waste and residues, such as manure, sewage sludge, or biodegradable waste. We produce biogas, nutrient products used in industrial processes, and biofertilizer for the local agriculture. These renewable products reduce climate impact and avoid exploitation of fossil fuels and minerals. This way, all our partners are joining the cycle, contributing to shift from a linear to a circular economy and reducing greenhouse gas emissions. Biogas is a renewable fuel for industry, maritime, and road transport. Biogas can help to reduce life cycle greenhouse gas emissions by up to 90% compared with fossil fuel use. Compared to fossil fuel, the biogas cycle does not add additional CO2 to the atmosphere. And if the biogas is produced out of manure, it is even possible to reach greenhouse gas emissions reductions beyond 100%. Gasum is continuously expanding the gas infrastructure, and as a customer, you can expect a reliable source of renewable energy. Our biogas is delivered in compressed or liquefied form to customers through pipelines, by trucks, or ships. We also offer bunkering possibilities out at sea. In a circular economy, waste and residues are not seen as a problem, but as raw materials for renewable energy that is competitive and available. So join the cycle and build a more sustainable future together with us.